So I want to. So we've talked a lot about sort of the foundations of Agda and how types and programming corresponds to logic. So I want to start showing you how to use Agda to do some things that you might actually want to do. So in particular, one of the things we've done in a previous homework was like taking certain functional programs and proving that they do what we want, that they're correct. I'm going to show you how we can actually, like a lot of those proofs that you did on paper on the homework, we can actually do them in Agda and have Agda be formally checking that our proofs are correct. Okay. So we're going to start out by, did we actually define addition on natural numbers? We did, right? We defined plus here. So just to show you, just to start out as an example of this kind of thing, let's prove that plus is associative, for example. That's a property that we would expect plus to have. So proving properties of functioning programs. So let's prove that plus is associative. So what should I write down as the type of the plus is associative, right? I want to write down a type that corresponds to the logical claim that plus is associative. Any ideas? Yeah.
Yes, maybe we should first define what does it mean to be associative, and then kind of get a type from that.
Oh, okay. We absolutely could, and we could define what it means for a certain operator to be associative, and then just say this is associative. I think for right now that's going to be a little bit overkill. Let's just directly write down the type that says plus is associative. We can think about abstracting it later. Well, yeah, go ahead.
Maybe I'm not sure.
Okay. I mean, how would I write it down, like, in some kind of predicate logic or something? Like, well, formally, what does it mean for something to be associative?
So, like, if you have like 3 elements together, you can add 2 and then add the other one, or you can first add and then add the other 2 ones.
Right, so something like x plus y plus z equals, okay. Yeah, and this is not quite complete yet, because what are x, y, and z? I have to...
For all.
Yeah, so I need like a for all. Say for all x, y, and z. This is true, right? So we're going to say like for all x, y, and z, which are natural numbers. Right, so this would be sort of how I would write it in logic. Now, do you all remember what does a for all correspond to in Agda? If I want to say for all x, which is a natural number. Did we talk about that? I think we might have mentioned it very briefly, but... Anyone remember?
It's a function which takes like x. So if it's a function which is dependent on x and then spits out, another function or a statement that is
Right.
true for any x you give.
Right. Yeah, so for all is really just a function. And we'll talk more about this probably tomorrow, but it's interesting seeing that actually there's a very close connection between for all and implication, which you don't, if you're just thinking about logic, you don't necessarily think of that. But for all is a kind of implication too. It says, if you give me and actually it's often stated that way. Sometimes you'll see things that say, if x is any natural number, then blah, 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 which is really a for all. But right, so this is basically going to be a function that can take x, y, and z and then return us a proof that, this expression equals this expression for that particular x, y, and z. But we can do this for any x, y, and z. Okay. So, I write this down in Agda as x, y, and I can This is an abbreviation, of course. I could write x colon nat, y colon nat, z colon nat. Then, okay, well this part, I just use our equality that we defined. Okay, that's it. So that's, oops, I don't want that to be commented out. Oops, what, could not, oh, okay. Because we've defined all these operators ourselves, and we haven't actually said what precedence level they have, we have to put parentheses and everything. There is a way in Agda to say, oh, this has precedence level, whatever. And pretty soon we're going to switch to using stuff from the standard library, and they all have. So we would not actually have to put all these parentheses if we were using stuff from the standard library. But, rather than go and figure out how to add those, we'll just live with the parentheses for now. Okay. So here, whoops, let's make this bigger. So here's our goal. I went ahead and filled in these arguments to the function, right? So I take 3 numbers and I have to return a proof that these things are equal. Okay, so here we go. This is our goal. Any thoughts on how we might proceed? Andrew?
We kind of like do what we do with induction and like choose a variable to like kind of base our like induction or proof on it, and like pattern match on that. Like X, you can pattern match on X.
Right, exactly. And here's, so, I mean, we often do that kind of thing, and here's kind of the thought process that could, or one possible thought process that could get you there. Say, well, I need to prove this, but I can't, if I just try to use reflexivity, it'll complain that it can't see that these are the same. So I need to do something that'll cause this to kind of reduce to the point where it can see that they're the same, right? And so then I ask myself, okay, well, it's kind of like plus can't reduce right now because plus, how is plus defined? But it actually pattern matches on its first argument, right? So if it knows that x is 0 or a successor, then plus can make some progress and reduce. And that would get this whole thing to make some progress. So not only does that tell us we need to do some pattern matching, that actually suggests which thing we should pattern match on, right? Because, in particular, because plus, where is it? Right? Plus pattern matches on that first argument. So, for example, pattern matching on z isn't going to help because plus doesn't care about that one. And so if we knew something about z, this wouldn't reduce at all. It would still be stuck trying to look at x. So let's pattern match on x. So I get a case for 0 and a case for successor. Okay. Well, in this case, right, once x becomes 0, the addition reduces a bunch, and we're just left with y plus z equals y plus z. So that's just reflexivity. Okay. How about this? So notice what happened, right? We had a successor here, and a plus of successor plus something, right? The successor kind of moves outside, and you just recursively add the leftover parts. And so that kind of happened twice here and once here, but now we've got a successor of something and successor of something, right? So forget for a minute about how we're going to convince Agda of this, but like, do you all believe that this is going to be true? And if so, why? Ivy, what do you think?
I believe it's true because through the math class that we've been through, we are taught that plus is associative, and because successor because that is inside the parentheses, it should be also associative.
So wait, what were you saying about successor again? I'm not sure I understood.
Because successor is being applied after the addition.
Right.
It should.
Okay.
It shouldn't
Yeah,
affect
it should. They should still be. If they were equal before, if you apply successor to both sides, they should still be equal. Right. Agreed. Okay. So there's actually a property of equality that we need here, which is that equality is a congruence, is the technical term for it, which says that if you have two things that are equal, if you do the same thing to both sides, you're going to end up with still equal things, right? It seems pretty. So we can actually prove that. So this is called Cong. And the way you would usually say this is, well, let's see. If I have, any types A and B, and if I have a function from A to B, any old function you like, and I have a proof that, I have some x and y that are equal, I guess I need to say what x and y are. So x and y are going to have type A. They're like the inputs to f. If x and y are equal, then also f applied to x is equal to f applied to y. Does this seem reasonable? I mean, this is a very, very general way of saying if you have an equation, you can do the same thing to both sides and it'll still be equal. Right? Now, this doesn't necessarily go the opposite way, right? If f is not an injective function, just because fx equals fy, I can't conclude that x equals y, but I can go this way. And this is very difficult to prove. There you go. I mean, it's the same as all the other properties of equality that we've proved, right? Where we pattern match, right? This proof, we pattern match on it and say the only thing this could be is REFL. And it's like, oh, I've now learned that x and y are literally the same. And so then over here, it like trend, this becomes like fx equals fx. And it's like, so this is this fact is already kind of built in somehow to Agda's idea of what equality means. All we had to do was kind of write it down. Okay. So we can use that in this case. We can say, well, look, I'm trying to show that successor of something equals successor of something. This has the form of the same thing applied to both sides of an equation, right? So, and that exactly matches the conclusion of this property. So if I apply congruence, and what's my function f going to be? Just successor, right? So if I say cong suck, right? Remember, these arguments to cong are all implicit arguments. I don't have to actually literally write them down. So the first thing I actually have to write is I have to tell it what f is going to be. And if I refine now, it's going to say yes, that works, and all you have left to show is I have to show this argument to Cong. So now I've reduced it to just showing that x plus y plus c is equal to x plus y plus c. And what do I do now? Yeah, Andrew?
Plus the soap.
Right. Exactly. So this is our induction hypothesis, if you want to think of it in terms of an inductive proof. Right? Again, same thing has happened here, where this is actually a different x than was in it's a different x than this argument, because we pattern matched on it and said, well, if it's a successor of something. So we have actually reduced it to a smaller case. And so if I say plus soak, maybe I can just do auto. Yep. Sometimes I'll also show you that if you're like, sometimes auto doesn't work, and maybe we'll run into a case like this later. You try auto and it's like, I don't know how to do this. There's only certain things it's willing to use by default, because if it tried to use anything possible, it would just there's way too many possibilities. But you can give it hints, and you can say, by the way, I think you should use plus a soak as a lemma. So please consider using that in your automatic proof. And then you do auto, and then you'll find it. In this case, it's already willing to make a recursive call, but maybe we'll see an example later where you have to give it a hint about what lemma to use. Okay. So that's a simple example. Did we define multiplication? We didn't. I'm trying to think of an example that's going to involve using transitivity, but maybe we'll just let it come up naturally. All right. Let's now define some lists, and then we'll prove some things about lists that we've actually done on the homework. Okay, so we'll make a type of lists. So list A or list set. Okay, so list takes a parameter which is a type called A, and it is a set, and we have two constructors. Empty list, which I'm going to write like that, and then cons, right? I'm going to make an infix version. So this is actually like if you say \:::, it makes this single character. It's like colon. I think we could actually just use that, but I don't know. The standard library defines it like this, so we'll use that. So this takes an A and a list A and makes a list A. Nothing too exciting there, but so I think one of the things you did on your homework was we proved that map of F compose G is equal to map F compose map G, right? So we're just going to we'll quickly define map, and we'll define composition, and then we'll see if we can actually give a proof of this. Okay. So map, of course, we'll have to say, for all types A and B, if you give me a function from A to B and a list of A, we can give a list of B, and map F X's is, well, of course, a pattern match on X's. And if it's empty, I say empty, and I can just do auto here, right? Whoops. Anyone see what happened?
So, don't you need to apply X on F and then
Yes,
cons there?
yes, indeed. So this is just to point out, I did that on purpose to point out, auto is great when you're proving logical things where there's kind of only one possible way to do it, or you don't actually care which proof you have, as long as you find a proof. But that's not the case here anymore. Right? As a logical statement, this says, for all types A and B, and for all functions F, and for all lists of type A, there exists a list of type B. As a logical statement, you can prove that by always returning the empty list. But that's not the function we want. We actually care which proof we have, if you want to say it that way. So auto will find something that has the right type, but it's not actually the thing we want in this case. So we're not going to do that. Oops, what just happened? I don't know. So yes, of course I want to say, fx cons map fx's. Okay, good. And then we can define function composition, which is going to say for all types A, B, and C, if I have a function from B to C and a function from A to B, then return a function from A to C. And this one I probably can do auto, because there's really only one way to implement this that makes the types work at all. And it's going to be the one I want, right? That's okay. So now we're going to write down, we'll call it, map comp. So I want to say, sometimes the way I write these things down, because there's like a lot of for alls you need to put first. So sometimes I'll just start by writing it like this. But if I tried to load this, it would say, I don't know what f and g are. So I'm like, okay, I need to go back and say, for all. So f, well, what type is f going to have? F is going to be like a function from b to c. And g is going to be a function from a to b. But then, okay, now what are a, b, and c? Well, they're arbitrary types. So I have to add some more for alls and say a, b, and c are set. Right, so this is the full type of it. For all types a, b, and c, for all functions f and g of appropriate types, mapping a composition is the same as map f compose map g. And I just realized I got myself into a pickle because to prove this as stated, we would actually have to say what we mean by two functions being equal. And I think on the homework I said, oh, you can prove the two functions are equal by showing that they have the same output for any input, right? It turns out, I don't want to go into why, because honestly I'm not even sure I completely understand why. That principle, called the principle of function extensionality, that functions are equal if they give the same output they give equal outputs for every possible input. That's not, you can't prove that in Agda by default. You can add it as an extra axiom, and it doesn't break anything to add it. But just to avoid having to deal with that, let's add an extra thing so we'll just bake in, applying it to any particular list. So if I have x's of type list of A, then we'll just say, okay, now we're getting too long. Move it down here. There we go. So I've now just baked in that extra step of saying, for all lists of A's, if you apply this function to that list, you're going to get the same list as things with okay. What do you think I should do first?
Maybe put too much on x's?
Pattern match on x's, right? That's a good idea. Why did you choose x's?
So that we can handle the case when all of them are empty strings, and then
Right.
handle the induction effect when all of them are not empty.
That's right. And that's exactly how we did the homework, right? We proved this by induction on lists, so it makes sense. So if I say x's in pattern match, okay, that actually, I wasn't expecting that to work, but the difficulty, the reason I was expecting some kind of difficulty is that x's is actually an implicit parameter, we haven't actually said x's on the left-hand side here, right? So we could solve that in a couple ways. One way is we could just say, actually, maybe we don't want it to be implicit. Maybe we want it to be a normal parameter. And that may actually be the right thing to do. I'm not really sure. Like which arguments to make implicit and which to make explicit, it kind of comes with experience. If you make too many things explicit, then it's really annoying to use everything because you're constantly having to pass all these arguments that Agda could figure out itself. On the other hand, when Agda can't figure out an argument that is implicit, you have to then use special syntax to like explicitly give an implicit argument, and that gets annoying. So, and I honestly don't have a good sense right now of with this particular theorem. If we ever use this theorem, would it be able to figure out what x's is or not? Maybe not. Just to make things simpler, let's just make x's into an explicit parameter so that we can pattern match on it more easily. But you can pattern match on implicit arguments. You just have to use some special curly brace syntax to refer to them. But if it comes up, if you need it, then we can talk about it. But yeah.
Would you define what implicitness and explicitness mean? Are you meaning in this case that we can still also do the same operation on things that are not lists? Like there might maybe be strings or
No.
what?
No. So this function, right? As a function, this has 1, 2, 3, 4, 5, 6 parameters, and then returns a proof that these things are equal, right? But all of these ones that are in curly braces, those are all implicit parameters, and this is an explicit parameter. And that means when we call the function, we don't have to actually write down these arguments. We're asking Agda to automatically figure out what those arguments have to be.
Okay.
And we're only going to explicitly give this one. Right. And the reason that is a big deal is that with dependent types, right, where the values of previous arguments can show up in the types of later ones, often it is possible to figure out what arguments should go earlier because like you can just read it off from the types of the later things. In a language that doesn't have dependent types, it's not really an issue because you can pretty much never figure out the right arguments because you don't have enough information to go on to figure them out. Okay? So our goal here, it doesn't look like reflexivity. However, if we sometimes so if we just say Control C, Control comma, it kind of, I don't know how it decides how much to reduce and stuff, but if you say I know this seems crazy. Control U is called a prefix argument in Emacs. It's often used to modify the behavior of some command by doing Control U first, and then, so a lot of commands have like some kind of standard variant that you can do by doing Control U, and some even have you Control U twice, and that's like a different variant. So I think a single Control U for this will say, oh, please don't reduce things. Just show me kind of like directly what it is. So if I just say Control U, Control C, Control comma, like this is literally what the goal is without actually doing any reduction. If I do Control U twice, then it tries very hard to reduce as much as possible. Right? In that case, it actually shows me, no, really, these both reduce to the empty list. And so I really can get away with reflexivity here. I mean, how it shows the goal to me doesn't affect what it's going to accept here. Because if I say reflexivity, then to see whether that works, it's going to try as hard as possible to reduce things to see if they're equal. So I don't have to worry about that. But and if I had just done auto here, like if you're not sure, you can always just try doing auto and be like, I hope this is reflexivity. And if it says reflexivity, then you're like, okay, I'm good. Okay. Now, what about this goal? So, again, telling it to reduce the goal as much as possible is going to be helpful here. Because if you look at this, you're like, this looks like this reduced some. This side, it looks like there's some more reduction that could happen, right? Because if we reduce the definition of composition, it's map F applied to map G of a cons, and map applied to a cons can definitely reduce, right? So there should be something that can happen there. Griffith, what's up?
Can you clarify about the commands? It's
Yeah.
Control U, Control U, Control C, Control comma?
Yes.
Okay, got it.
Mm-hmm. So, yes, that did more reduction. Okay, this is looking better because I've got like something here that looks similar. Okay. Right, and you should be, at this point, this should remind you of what we did when we were proving the associativity of plus, where we ended up with a goal that said you have to prove that successor of something equals successor of something, right? And so here I've got blah of something equals the same blah of something, right? So this is congruence again. I want to say, yeah, if I can just show that these inside parts are the same, that proves that this whole thing is the same, because these parts are the same. Okay. So I can say congruence, and I have to say what function I'm applying to both sides. So what was that?
Function is a map, right?
No, the thing that's being applied to both sides of the equality is like consing this onto, right? So what I really want to say is if I can just show that equality, and then if I apply this function to both sides, I'll get this equality, right? So there's a few ways I could write this. I could write it with a lambda. I could say, oh, it's lambda, R F G X cons R, right? That's the function that I'm applying to both sides. Like take whatever that thing is, and then give me F G X cons whatever that thing is. I could also actually just write, this is really just partially applying cons to its first argument. So I could just say, like that. I have to write.
Just that right now is what you can use?
Yep. Because, so I'm writing cons with the underscores, that turns it into like the name of a function that you can apply to some arguments that come after it, instead of writing it infix. So I'm saying this function applied to this argument, and that of course will be a function that's expecting the second argument. Ivy?
Could you also write it like f of gx cons and not apply it to the second argument?
I don't believe that syntax works in Agda. That would work in Haskell, right? So in Haskell, when we have binary operators, you can write, argument, operator, and then put it in parentheses, and it's like the function that's expecting the other argument. But because Agda allows it doesn't just have binary operators, it allows like arbitrary, you could have like a ternary operator that's got like underscore, symbol, something else. We could try it, but I'm pretty sure it's not going to work. Yeah, it doesn't even parse. So, but this is going to work. So this is nice in this case, but in the general case, you can just put a lambda and just say lambda r, and then pick out whatever part is the same, and then put the r in the part that's going to change.
Could
Okay?
you also write it like that way, like in a comment?
Yes, absolutely. In fact, I'll write it this way here, and then I'll put this in a comment. So, because this is like.
So which is better? Should you recommend?
When you get used to it, if you're doing a lot of proofs with lists, like you'll often do something like this, and it's maybe a little faster to type. This is more general though. Like you're always going to be able to write cong if you need to provide some function to pick out which part is you're applying to both sides of the equality. You can always write it as a lambda. So I don't know what that means. Which one is better, but
And what does the R mean?
the R. So remember that I have to use congruence. I have to say, oh, it's not on the screen anymore, is it? I have to provide this function f that says if you can prove x equals y, then you can prove that f applied to both sides of that is also equal. So I'm saying what my f is, right? What is the thing that I'm doing to both sides? So r represents like either side of the original equality, the x and y up there. And then this is like what I end up with by doing this same thing to both sides. I don't know why. I often use the letter R, but I couldn't tell you why. Maybe because I rarely use that letter for other things, and so I don't know. Why do I use R? I don't know. You can call it X, but I'm already using X. You can call it yeah, R for result, but I don't know why you'd call it result. Yeah, S for side. I don't know. R for right. Right of the, but it doesn't necessarily have to be on the right. Well, in this case, yeah.
That's kind of on the left.
Yeah, well, you're talking about the left and right of the equality. I mean, that's not in scope F. Oh, right. So, okay, good. This gives us an opportunity to see how we can bring some implicit arguments into scope. Because sometimes, as in this case, I think we really do want f and g to be implicit. I think it's going to be annoying every time we want to use this theorem to have to explicitly say what f and g are. However, when we're proving it, we actually need to refer to f and g, as in this case. And I tried providing this, and it said, yeah, no, I don't know what f is. There's nothing named f that's anywhere in scope, right? So, note, f is defined up here in the type, but that just scopes over the rest of the type. So in the rest of the type, I could have referred to f. But, well, I do, right? I do refer to f in the rest of the type. But down here, in each clause, f is not defined. So one way you can do it is just, you literally, every time you put curly braces, that's like it goes one by one, argument by argument. So this corresponds to A, but I don't care about that one, so I could put underscore, right? And then I could, do underscore, underscore, and then put F, all right? And then I could put G. Okay, so that works. That's one way to do it. And I'm going to comment that out and show you a different way. Excuse me. So what I'd really like to say is, yeah, the thing that is called f in the type, I want that one. I don't want to have to write ABC. So I can say f equals, and then I can give it whatever, I can pattern match on it or give it whatever name I want. In this case, I don't have any better name to call it than f. So I might as well just say f equals f, which looks a little strange, but right, this is saying the argument I want is the one that's called f in the type, and I'm going to call it f also here. And I can do the same thing for g. So I don't know which is better. I mean, it's not necessarily that much shorter in terms of number of characters than this way. But I don't know, this is just annoying. Also, to do this, you have to count. And if I ever added more arguments, this would suddenly break, but this would still work. So I usually prefer doing it with the names. Okay, after all of that, we now have to prove this. But that's easy. That's our induction hypothesis, right? Because this is now for a smaller list x's. And so I can say, well, I can probably say auto, actually. That's it, map comp x's.
Was that Control A?
Control C, Control A, yep. So there we go. We have actually proved that map distributes over function composition. Other questions at this point?
we're like writing our proofs, or like trying to write our proofs in Agda like this,
Mm-hmm.
do we need to have like, do we need to be like trying to follow like the proof we have written out, or like try to like have Agda kind of guide us?
Well,
or-
you can do it either way. And so actually I'm going to show you, let's see if we have time to start now. Maybe we'll do it for a few minutes. So in this particular case, this one is easy enough, I think, that you could just let Agda guide you, right? You could literally just say, okay, what do I have to prove? Oh, look, that looks like I should use congruence. Like, oh, look, that's the induction hypothesis done, right? However, for something where the proof is longer, especially when the proof involves using transitivity of equality, where I've got like a bunch of multiple steps that, say this is equal to this is equal to this is equal to this, it's not going to be obvious just from looking at what Agda says you have to prove that you have to do that, right? And so I'm going to show you it's actually possible to give a very different style of proof of the same thing that looks a lot more like the kinds of proofs that we've been writing, where I say this is equal to this and here's the reason why, and this is equal to this and here's the reason. Even using the same syntax. So you can often get pretty far just letting Agda guide you, but we'll see there's also other ways of going about things. Other questions? Do you have a question, Griffith?
Thought I did. But now I'm looking at the top of the screen and that's my question. I was very confused about how this fit into the whole proving plus this stuff, and I was like, oh wait, it's proving an entirely different thing. That's why plus is mentioned.
Right.
I was all flipped around.
Indeed. No, I mean I proved that plus is associative first just as a simpler example of proving a property of a program that we wrote. Yes. But in a sense, it followed a similar kind of pattern, right? That we needed congruence, and then we did the induction hypothesis. We could prove, if you wanted to prove something more analogous, you could prove that a pending list is associative, and that would actually have a very similar structure as well.
Question.
Yeah.
In Agda, we can think of numbers as functions, like we did in lambda calculus. I mean, because we always say it's a successor of some sort.
Mhm.
Like we don't see them as numbers, like we know them in Haskell or something. Like, is it like always a requirement to think of them that way, or?
We're not thinking of numbers as functions in Agda. They're not.
It says suck of n.
Yeah.
What do you
That,
mean?
This means like plus one of another number. So
Right.
0 is like the first number we know about. Then we say, well, I can add 1 to it, so let's call it 1.
Right.
I can add 1 to it, so let's call that 2.
that's right. We're actually building them up as an algebraic data type, right? A number is actually a thing that can be either 0 or it could be successor of successor of successor of something. It is not actually a function, though. It's just it is literally a thing, because Agda does have built-in data types, and so we can actually define them that way, right? We define them as functions that do something a certain number of times in lambda calculus, because we didn't have algebraic data types, so we needed to encode things as everything as a function. But if you don't have to do that, why would you?
So if you call like type of 5, is it gonna say 5 is gonna say suck of suck of suck of suck?
That's what 5 is equal to, but it won't show it that way because we told it that these natural number things, like those are really the numbers, and so please use some magic syntax and stuff for them. But I mean, if I say, you know, suck of 0, right, that's 5.